Hey guys, welcome back to another video. First of all, I want to introduce myself. My name is Mamta from BSc Chemistry honors second year. Today I today I make a video for visually impaired students. Today I will teach you organic chemistry. Read out organic chemistry chapter, which book is modern book's author is Dr. G.M. Sehgal. So my topic is nitro compounds. Nitro compounds. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atom by nitro groups. Nitroarenes Nitroarenes can be prepared rather easily and have been used synthetic reagents since long, but nowadays even nitroalkanes are being prepared and used on a large scale. Structure of nitro groups. Nitro groups is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen or nitro group, but actually nitro group is stabilized by resonance and is a hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen oxygen bond is 121 picometer or 1.21 angstrom, which is intermediate between NO single bond length and NO double bonded length. In case of nitroarenes, resonance of nitro groups with the ring can also take place, giving rise to additional contributing structures for the molecules. It will be interesting to note that nitro group is isoelectric with carboxylate anion. Nomenclature of the compounds. Nitro compounds are named by writing the words nitro before the name of the parent compound. The number of nitro groups and their positions are also suitably indicated as isolated below. Nitromethanes, nitroethanes, nitropropanes, 2-nitro-3-methyl-butane. Classification of nitroalkanes. Nitroalkanes are termed as primary, secondary, or tertiary according as the nitro group is attached to a primary, secondary, or tertiary carbon atom. That is, primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. For example, nitroethane, primary nitroethane, secondary 2-nitropropane, 2-methyl 2-nitropropane. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by the following methods: vapor phase nitration of alkanes. The reaction involves the substitution of hydrogen atoms of the alkane by a nitro group is carried out in the vapor state by heating the alkane with the nitric acid at about 700 Kelvin temperature. Limitation of the process. During the nitration of higher alkanes, all possible isomeric nitro products are formed. More rupture of the carbon-carbon bonds also takes place, leading to the formation of nitroalkanes containing lesser number of the carbon atoms. For example, nitration of propane result in the formation of a mixture of four nitro compounds as shown below. Due to the formation of complex mixture of the products, this method is not used for laboratory preparation of nitroalkanes. However, the method is widely used for the commercial preparation of nitroalkanes. Mechanism: the reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Action of silver nitrite on alkyl halides: this is the method generally employed for the laboratory preparation of nitroalkanes. When heated with the silver nitrite, alkyl halides undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitriles. This is because nitro is an abundant nucleophile. However, the mixture of alkyl nitriles or nitroalkanes can be separated by fractional distillation. Oxidation of amines: when an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Preparation of nitroarenes: nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agents generally used are concentrated or fuming nitric acid, mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. This mixture is the most commonly used as a nitrating agent. Mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Acetyl nitrite obtained by mixing nitrogen pentoxide and acetic anhydride, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent: the choice of nitrating agent to be used for nitration of a given compound depends upon the following two factors: nature of compounds to be nitrated, number of nitro groups to be introduced. In the nitration of aromatic compounds containing electrons releasing or activating groups such as ammonia, hydroxyl group, methane, the reactions takes place readily at room temperature by employing concentrated HNO3. In some cases, even diluted HNO3 can be used. For example, phenol in reaction in phenol. For nitrating compounds containing electron attaching or deactivating groups such as COOH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and metadinitrobenzene, for instance, can be obtained from the benzene under the conditions shown below. Mechanism of the nitration: nitration of aromatic compounds, like other aromatic substitutions reactions, is electrophilic in nature and involves a nitronium ion as attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with the nitric acid sulfuric acid mixtures. Generation of electrophile: formation of carbocations, proton transfer from the carbocations to yield the final product. Evidence in favor of the above mechanism: it has been shown above that aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as an electrophilic reagent, is generated in a preliminary steps and brings about further reaction in two steps. The first step is a slow rate determining steps involving a addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage CH bond. This mechanism has been fully supported by isotope tracker technique as explained below. If an aromatic compound labeled with the deuterium The heavier isotopes of hydrogen having a mass of 2 atomic mass unit is subjected to nitration. It is found that the rate of substitution of the deuterium is the same as that of ordinary hydrogen or protium. In other words, no isotopes effect is observed. Since a carbon deuterium bond is broken more slowly than carbon protium bond, the absence of the isotopes effect in the aromatic nitration can be justified only if the rate determining step of the reactions does not involve any cleavage of the carbon hydrogen bond. This means that the final steps involving the abstractions of proton through the cleavage of carbon hydrogen bond cannot be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining steps, as it does not involve any cleavage of carbon hydrogen bond. Once formed, the carbocations loses the proton relatively as fast to form the final product. The absence of isotopes effects also rules out the possibility of single step mechanism of the nitration. This is because this is because the single step substitution cannot take place without the cleavage of carbon hydrogen bond. As such, it must exhibit isotopes effect, but this is not so in actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is rate determining steps. Comparison of nitration of arenes and nitration of alkanes. It may be noted that the nitration of arenes takes place at relatively low temperature, whereas the nitration of alkanes requires a very high temperature. This may be due to the fact that nitration of arenes involves the initial formation of an electrophilic reagent, while the nitration of alkanes is supposed to involve the initial formation of free radical. The formation of free radical takes place through homolysis and requires stronger condition than the formation of electrophile, which takes place through heterolysis. As such, nitration of arenes takes place more easily than nitration of alkanes. Nitroarenes cannot be prepared by the action of silver nitrile or aryl halides because of the very low reactivity of aryl halides towards nucleophilic reagents. Physical properties of nitro compounds. Physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smells and are sparingly soluble in water, with the exceptions of a few compounds, including nitrobenzene, which are yellow, oily liquids. All other aromatic nitro compounds are yellow crystallized solids. Nitrobenzene has an odor of bitter almonds and is known as oil of myrrhine. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in the water, while aromatic nitro compounds are insoluble in it. They are, they are however readily soluble in organic solvents such as alcohol and ether. Stability. When heated strongly, polynitro compounds decomposes with the explosive violence. Boiling points. Due to the presence of highly polar nitro compounds in their molecules, nitro compounds have strong dipole-dipole interactions. Consequently, they possess high boiling points, much higher than hydrocarbons of comparable molecular masses. However, most of the nitro compounds are volatile in steam. The melting and the boiling point of the nitro compounds gradually increases with the number of nitro groups, as is illustrated ahead. Nitrobenzene. Chemical reaction of nitroalkanes. The important chemical reaction of nitroalkanes are as follows: acidic nature, tautomerism. Nitroalkanes containing a alpha hydrogen atom, that is primary and secondary nitroalkanes, only exhibit acidic behavior and form salt in the presence of strong alkali. For example, these reactions. The acidity can be attributed to the fact that nitro compounds has a strong electron withdrawing inductive effect. The anion formation after the removal of the proton from nitroalkanes gets resonance stabilized due to the ability of nitro groups to accommodate negative charge as shown below. It is interesting to note that if salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkanes do not separate immediately, but we get another form of nitroalkanes known as acinitro form, which slowly changes into nitro form. This is due to the fact that primary and secondary nitroalkanes exhibit tautomerism. The tautomeric forms being nitroforms, acinitroforms. The tautomeric equilibrium between the two forms lies almost completely towards the nitroform because it is stabilized by the resonance of the nitro groups. Acinitroform is relatively stronger acid than nitroforms. An important feature of acinitroform that is it can act both as an electrophile and a nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes do not have any alpha hydrogen atoms. As such, they exhibit neither acidic characters nor tautomerism. Reduction of the alkenes. Reduction of nitro compounds is the one of their most important reactions. The reduction of the nitro compounds nitro groups takes place in stage as shown below. नाइट्रो कंपाउंड से पहले नाइट्रोसो कंपाउंड्स बनेगा, फिर सब्सटीट्यूटेड हाइड्रोक्सल अमाइन बनेगा, फिर प्राइमरी अमाइन बनेगा. The product actually obtained depends upon the nature of the reducing agent and pH of the reaction medium. Thus, nitroalkanes can form different products and reduction as given below. Reduction in the acidic medium. When reduced in an acidic solution, nitroalkanes forms primary amines. Catalytic reduction or reduction with lithium aluminum hydride. Reduction with lithium aluminum hydride or H2 in the presence of nickel palladium or platinum catalysts also yields the same products. Reduction in neutral medium. If the reduction is carried out in a neutral solution, a hydroxylamine derivative is obtained. The hydroxyl amines are readily oxidized to corresponding nitroso compounds on warming. The Tolleans reagents which gets reduced to metallic silver. This reaction is used a test for nitro compounds under the name Baker-Millikan test. Hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergoes hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine, for example, nitroalkanes. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. Nitroalkanes. Tertiary nitroalkanes are not hydrolyzed by acid. NEF reactions. When sodium salt of primary and secondary nitroalkanes are hydrolyzed by boiling with the dilute sulfuric acid, aldehyde and ketones respectively are obtained. The reaction proceeds through the acid-nitro form of nitroalkanes. For example, these aldehydes, primary secondary nitroalkanes. In this reaction, the acid-nitro forms of act as the electrophile. Action with the nitrous acid. Primary, secondary, and tertiary nitroalkanes exhibit different behavior towards nitrous acid. Primary nitroalkanes reacts with the nitrous acid to form nitrolic acids which dissolve in NaOH to produce a red solutions. Secondary nitroalkanes react with the nitrous acid to form pseudonitrols which have blue color but do not dissolve in the NaOH. Tertiary nitroalkanes and nitroarenes do not react with the nitrous acid since they do not contain any alpha hydrogen atom. The above reactions can be used for distinguish between primary, secondary and tertiary nitro compounds. Halogenation: when treated with halogens in slightly alkaline solution, primary and secondary nitroalkanes undergo halogen at alpha positions. For example, nitroethane. Nitromethane on the chlorination in alkaline medium gives trichloronitromethane, also known as chloropicrin. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogen atom condensation with the aldehyde due to the presence of active alpha hydrogen atom in them. Primary and secondary nitroalkanes undergo aldol type condensation with aldehydes in the presence of a base to form nitroalcohols. For example, एसिटाल्डिहाइड नाइट्रोएथेन के साथ रिएक्ट करके 3 नाइट्रो ट्यूब्यूटेनॉल बनाएगा. The reactions 6 and 7 proceeds through the acenitroforms which acts as a nucleophile in these reactions. Manganese reactions. This is the condensation reactions which involves the formaldehyde, ammonia or a primary or secondary amines and a compound having at least one active hydrogen such as primary and secondary nitroalkanes. For example ये हमारा बनेगा nitroamine hydrochloride. The reaction can be used for preparing nitroamines, diamines, etc. Chemical reaction of nitroarenes. Nitroarenes are chemically rather inert compounds. The nitro group is firmly attached to the reduced and cannot be replaced by other atoms or groups under ordinary conditions. The important reactions are as follows: acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro groups attached to the benzene ring are somewhat acidic in nature due to the strong electron withdrawing effect of the nitro groups on the benzene ring. Reduction: the most significant reaction of the nitro compounds in their reductions under different conditions to give different products. As already stated, the reactions takes place in stage and the nature of the final product depends mainly on the pH of the reaction mixture. We will illustrate the reduction of nitroarenes under different conditions with the help of nitrobenzene. Reduction in acidic medium. On reduction in acidic medium with an active metal and acid such as zinc and HCl or tin and HCl, nitrobenzene yields aniline. Nitrobenzene further heated with in the presence of zinc and HCl form aniline. Mechanism. The mechanism of the proposed for the reaction involves a number of steps in which addition of electrons and protons takes place and the nitrobenzene's free radical anion and nitrobenzene's free radical anion are formed intermediates. The mechanism may be summed up as follows these types. Catalytic reduction. Reduction of nitrobenzene with H2 in the presence of nickel platinum catalyst also leads to the formation of aniline. Reduction in natural medium. When reduced in the natural medium, example with zinc dust and the ammonium chloride solution, the reaction stops at the hydroxylamine stage. Reduction with the alkaline medium. On reduction in alkaline medium, nitrobenzene yields different products depending upon the nature of the reducing agent employed. These types hydrobenzene. These products are actually formed by the further reactions between the primary reduction products, that is nitrosobenzene and the phenyl hydroxylamine as shown below. Azoxybenzene is formed by the condensation of nitrosobenzene and phenyl hydroxylamines as given below. Reactions. There is sufficient evidence to show that azobenzene is formed through the intermediate formation of azobenzene and its further reductions. Hydroxybenzene is similarly formed by the further reduction of azobenzene. Reduction with lithium aluminum hydride. Reduction of nitrobenzene with lithium aluminum hydride also yields azobenzene. Electrolytic reduction. When reduced electrolytically in the weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic solution, nitrobenzene yields para-aminophenol. Due to the rearrangement of the phenyl hydroxylamine first formed, electrolytic reduction in alkaline medium yields azobenzene and hydroxybenzene. Selective reduction. In case of compounds containing more than one nitro group, it is possible to carry out the selective reduction of the one of the groups by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. For example, meta-dinitrobenzene forms meta-nitroaniline. This reduction is known as Ginin reduction. Electrophilic substitution. Nitro group, being an electron withdrawing group, has a strongly deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under strong condition, nitro compounds may undergo electrophilic substitution in meta position with respect to the nitro group. For example, metachloronitrobenzene with reacts with the form meta-nitrobenzene sulfonic acids. It may be noted that nitrobenzene does not undergo Friedel-Crafts reactions. Nucleophilic substitution. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this is very electron withdrawing influence of the nitro groups makes the benzene nucleus liable to attacked by nucleophilic reagents. Thus, unlike benzene, nitrobenzene or heating with the sodium hydroxide gives small amount of the ortho and para-nitrophenols. Mechanism. The mechanism of the reactions may be outlined as follows by considering the formation of para-nitrophenols. ये इस प्रकार से हमारी इलेक्ट्रॉन्स की मोशन होगा, किस प्रकार से इलेक्ट्रॉन घूमेंगे. Replacement of the nitro groups in case of polynitro compounds on other nitro compounds itself can be replaced by nucleophilic groups. For example, para-dinitrobenzene. Thank you so much.